This homework assignment is focused on aldehyde and ketone naming as well as Grignard reactions. So for the first question, we're asked to give the IUPAC name for the following aldehydes, looking at the length of the carbon chain, incorporating the aldehyde functional group. We have carbon number 1, 2, 3, 4, 5, so 5 carbons. So pentane, we take off the E and add Al to specify the aldehyde functional group, which, similar to carboxylic acid, will always be at the 1 position because that terminates the end of the carbon chain, because we always have hydrogen attached to that carbon, as well as the double bond oxygen. In this case, we have a nice propyl group at the end, so it's going to be a dimethyl, 2 methyl groups, and this carbon right here has a stereocenter. So for the ranking, so this is going to rank first, that one's second, that one's third. So it looks like we have a clockwise rotation, or an R stereocenter. All right, so this is R. We only have one stereocenter, so we're going to specify the carbon. At carbon number 3 and 4, we have methyl, so R, and then 3, 4, dimethyl, and pentane, but take off the E and add Al to specify the aldehyde functional group at the 1 position on the carbon chain. For this, we have a similar situation. We've got 1, 2, 3, 4, 5, 6 carbons though, so this is going to be hexanal. And then it looks like we have a stereocenter at carbon number 3 again, not carbon number 4, because on carbon number 4 we have 2 ethyl groups. So at carbon number 3, for ranking all the substituents, CH2 equals CH2. Carbon double bond oxygen definitely beats CH3. But beating both of those, beating the CH2s is our CH. So we're ranked 1, 2, 3. So this is a clockwise rotation, but 4 is our hydrogen, which is facing toward us. All right, so 4 is our hydrogen facing toward us. So even though we have a clockwise rotation, it's an S stereocenter. So this one is going to be 3S, or just S. And then in this case, we have 2 ethyl groups, so an ethyl group at the 3 and at the 4 position. So 3, 4, diethyl hexanal. All right, for the next one, we've got ketone functional groups. Here we have a 1, 2, 3, 4, 5 carbon chain. We've got a methyl group at carbon number 2 and carbon number 4. So this is going to be 2, 4, dimethyl, and then 1, 2, 3, 4, 5 carbon chain. We have a ketone at the 3 position, so 3 pentanone. So instead of pentane, we take off the E and add an O in E for the ketone. And again, for the aldehyde, we take off the E and add an Al for the aldehyde. All right, and then for the next compound, we have a 1, 2, 3, 4, 5, 6 carbon chain. We've got bromine at carbon number 2, chlorine at carbon number 4, and our ketone at carbon number 3. So 1, 2, 3, 4, 5, 6 carbon chain. So this is hexanone, and we've got 2 bromo, 4 chloryl, and we have 2 stereocenters on this compound. So I'll draw my hydrogens in there and there. For this stereocenter here, chlorine wins, then our carbonyl carbon, then our ethyl group. So 1, 2, 3, so this is a counterclockwise rotation, but 4 is in front, so it's actually R instead of S. Here, 4 is in the back, which is convenient. That's 1, bromine wins, then our carbonyl carbon, then our methyl group. So that is also a clockwise rotation. So we've got 2R, 4R, and then we have bromine at the 2 position, 2 bromo, and then 4-chloro, and again we have 1, 2, 3, 4, 5, 6 carbons, so this is going to be 3-hexanone. So 2R, 4R, 2-bromo, 4-chloro, 3-hexanone. This could also be 4-chlorohexane, 3-one. You can put the 3 out front or right in front of the ONE. Alright, this is a little bit of a review, but just reincorporating the aldehyde and ketone functional group, rank the compound with the highest boiling point. It's definitely going to be our 1, 2, 3, 4, 5 carbon chain with a carboxylic acid functional group because it has the most hydrogen bonding potential. One thing I need to point out is when you have that hydrogen on the carbonyl carbon, that hydrogen does not have hydrogen bonding potential. It's also not an acidic proton. So that's often confused when you're looking at different reactions with our aldehyde functional groups. Again, it is not an acidic proton and it does not have hydrogen bonding potential. Alright, to explain a short reaction where a Grignard reagent is used and on a compound with a carboxylic acid functional group. So let's have a compound with a carboxylic acid functional group like acetic acid or ethanoic acid and have our, let's say, CH3MgBr, so our Grignard reagent's already prepared. In the second step, we'd work it up with an acid like H3O+. In this case, once we have our Grignard reagent, we have our nucleophilic carbon, specifically our methyl group. If we have an acidic proton, what's going to happen is our Grignard reagent is going to take that and lead us to formation of a conjugate base. And then our reactive carbon chain in our Grignard reagent is just simply protonated. So our other product is going to be now CH4. So now we just simply have a methyl group, which is no longer reactive at all. So all we're going to do is an acid-base reaction, deprotonate that. If we work it up with water, so if we work it up with H3O+, then we'll do a proton transfer reaction, and we'll get right back to our starting material. So the reason why we don't use the Grignard reagent in solvents such as water or ethanol is because that same proton transfer reaction would happen. So if we have let me draw the Grignard reagent differently this time. So if we have something like an ethyl group attached to a Grignard reagent, so my electrons are here that would attack, we could add an ethyl group, and we have a solvent such as ethanol in solution, then what's going to happen is instead of reacting with our reactive carbonyl carbon, so let's say we have 1, 2, 3, 4, 5, so we've got 2-pentanone here. Instead of doing a nucleophilic attack on our 2-pentanone, if we have a more abundant solvent in solution, then our Grignard reagent again is just going to do a proton transfer on our solvent, leaving us with ethane, so just CH3CH3, and that is the end of the reaction. So our 2-pentanone, what our goal for our addition was, is not going to react. Alright, 4-5, draw the mechanism and predict the products for the following reactions. So here our Grignard reagent is going to attack our carbonyl carbon. It's going to push these electrons up to the oxygen and get us to our intermediate, which is now our cyclopentane ring. And now our double bonded oxygen is a single bonded oxygen with a negative charge on it, and we've added our isopropyl group. And we have a negative charge in the oxygen. We could say that MgBr is next to it, so now there's a positive charge in the magnesium, so we could say MgBr is right there if you wanted to, or you can just leave it out. Either way would be fine. Importantly, we do have our isopropyl group attached, but we need to protonate this to get us to our final product, so we're going to add H3O+ to do our workup. And notice this is specified in step 2. If we mixed all of these things together, all we do is protonate this and basically make propane out of our Grignard reagent, and we'd still have our ketone. So this is specified in two different steps because essentially once our Grignard reaction is done, once we've fully formed this intermediate, now we can do a workup and protonate our alkoxide anion intermediate using our H3O+. So that'll get us to our final product, which I'll draw up here now, which we've converted our ketone to an alcohol functional group. So we've got OH and then our isopropyl group. So that is the mechanism and products for the reaction. All right, for the next one, we are going to do pretty much the exact same thing, except now it's going to be CH2CH3, which is added, rather than an isopropyl group, which is added. So if we imagine our electrons, and this is drawn a little bit differently, I'm going to draw it over here this time. So we could have our isopropyl group, or sorry, our ethyl group, not our isopropyl group, that was up here. If we have our ethyl group, we could say we have a lone pair of electrons on that carbon, and that's somewhat stabilized by our magnesium of our Grignard reagent. So our nucleophilic attack is coming from this carbon here. So here, if we do our nucleophilic attack on that carbon, that gets us again to our intermediate, which is our cyclopentane ring. And now we've attached an ethyl group, and now we have our oxygen with a negative charge. This is going to do, and one more time, just let's look at this and clarify. So my carbon here had the lone pair of electrons on it. That was my nucleophile. So that carbon right there is this carbon right here. That carbon right there, which was my nucleophile, which attacked that carbon, formed that bond that we just talked about. This is the CH3 that was attached to that carbon. So that CH3 right there is that CH3 right there. All right, same as before, we're going to do a workup with our acid H3O+. So my electrons are going to take that proton. Those electrons are going to go there. That's going to get us to our final product, which is our cyclopentane ring. And we have an alcohol functional group, and we have an ethyl group. For the Grignard reaction, we're always going to convert a ketone functional group to an alcohol functional group, specifically if we do an acidic workup. Now with this, we could do a slightly different workup. We'll talk about that in class, but if we have essentially a alkyl halide, then our oxygen with a negative charge could attack that, and we could actually form an ester. All right, for the next question, this mechanism is a little bit longer. Now we have two equivalents of our Grignard reagent. So here the electrons are going to attack our carbonyl carbon and push these electrons up. That gets us to our intermediate, where now we have oxygen with a negative charge, and we have chlorine, and we have attached our ethyl group again. In the next step, we're not going to add our H3O+ yet, but what's going to happen is that our electrons from our oxygen with a negative charge are going to come back down. We're going to kick off our chlorine, and we're going to form a ketone functional group. So here we have 1, 2, 3, 4 carbons in our chain. 1, 2, 3, 4 carbons in our chain. We formed a ketone functional group. And now we have another equivalent of our Grignard reagent. So again, we have our ethyl with our MgBr there. Our electrons here are going to attack our carbonyl carbon again and push those electrons up to get us to our next intermediate, which now we have our oxygen with our negative charge. We have added another ethyl group, and we still have our original ethyl group in our carbon chain. Now we can do a workup where we add H3O+. So these electrons here are going to take that proton and break that bond to get us to our final product, which is our 4-carbon chain. Now we have an alcohol functional group here, and now we have another ethyl group attached there. So that is the final product for this reaction. All right, now we have an aldehyde functional group. So we would have a hydrogen off here. It wasn't drawn. Those are optional to draw. You can draw them if you want. So with our aldehyde functional group, we have our Grignard reagent. We're going to attack the carbonyl carbon, push those electrons up to get us to our intermediate, which now is an oxygen with a negative charge. Once we push those electrons up, let's just clarify what's attached here now. So we've added our ethyl group. So that is the ethyl group that we've added and formed that bond there. We also have a hydrogen attached to this, so those are the 4 things attached. When these electrons come back down, there's nothing available for it to kick off. Our hydride anion is not stable enough to easily kick off like our chloride anion was. So that means we are stopped there. Even if we had 2 equivalents of our Grignard reagent, we would still stop there. So now we do a workup with water, so with H3O+,